The Internals of Postgres. Chapter 8, Buffer Manager. A buffer manager manages data transfers between shared memory and persistent storage and can have a significant impact on the performance of the database management system. The Postgres Buffer Manager works very efficiently. In this chapter, the Postgres Buffer Manager is described. The first section provides an overview, and the subsequent sections describe the following topics: Buffer Manager structure, Buffer Manager locks, how the Buffer Manager works, ring buffer, and flushing of dirty pages. Figure 8.1. Relations between Buffer Manager, storage, and backend process. Shared buffer pool. Storage. Backend process. 8.1. Overview. 8.1.1. Buffer Manager structure. The Postgres Buffer Manager comprises a buffer table, buffer descriptors, and buffer pool, which are described in the next section. The buffer pool layer stores data file pages such as tables, indexes, as well as free space maps and visibility maps. The buffer pool is an array, i.e., each slot stores one page of a data file. Indices of a buffer pool array are referred to as buffer IDs. Section 8.2 and 8.3 describe the details of the Buffer Manager internals. 8.1.2 Buffer Tag. In Postgres, each page of all data files can be assigned a unique tag, i.e. a buffer tag. When the Buffer Manager receives a request, Postgres uses the buffer tag of the desired page. The buffer tag comprises three values: the rel file node and the fork number of the relation. The rel file node and the fork number of the relation to which its page belongs, and the block number of its page. The fork numbers of tables, free space maps, and visibility maps are defined in 0, 1, and 2, respectively. For example, the buffer tag 1682.1, 1638.4, 37.72.1, 07 identifies the page that is in the 7th block whose relation OID and fork number are 37.21 and 0 respectively. It's the relation's OID, and then the fork number. The relation is contained in the database whose OID is 1638.4 under the table space whose OID is 16.821. Similarly, the buffer tag 1682.1, 1638.4, 37.72.1, 1, 3. So 1 is the fork number, and 3 is the third page, or third block of the free space map, whose OID and fork number are 37.72, 1 and 1, respectively. 8.1.3 How a backend process reads pages. This subsection describes how a backend process reads a page from the Buffer Manager. When reading a table or index page, a backend process sends a request that includes the page's buffer tag to the Buffer Manager. The buffer manager returns the buffer ID of the slot that stores the requested page. If the requested page is not stored in the buffer pool, the buffer manager loads the page from persistent storage to one of the buffer pool's slots, then returns the buffer ID's slot. The backend process then accesses the buffer ID's slot to read the desired page. Seems like you could send the page along with the buffer ID, right? And then step 2 and 3 could be the same. Except maybe sometimes you don't need to send it. When a backend process modifies a page in the buffer pool, e.g. by inserting tuples, the modified page, which has not yet been flushed to storage, is referred to as a dirty page. 8.1.4 Page Replacement Algorithm. When all buffer pool slots are occupied, but the requested page is not stored, the buffer manager must select one page in the buffer pool that will be replaced by the requested page. Typically, in the field of computer science, page selection algorithms are called page replacement algorithms, and the selected page is referred to as a victim page. Research on page replacement algorithms has been ongoing since the advent of computer science. Thus, many replacement algorithms have been proposed previously. Since version 8.1, Postgres has used clock sweep because it is simpler and more efficient than the least recently used algorithm used in previous versions. 8.1.5 Flushing dirty pages. Dirty pages should eventually be flushed to storage. However, the buffer manager requires help to perform this task. In Postgres, two background processes, checkpointer and background writer, are responsible for this task. Direct I/O. Postgres does not support direct I/O, though sometimes it has been discussed. 8.2 Buffer Manager Structure. The Postgres Buffer Manager comprises 3 layers: the buffer table, buffer descriptors, and buffer pool. See Figure 8.3. 3 layers: buffer table, buffer descriptors, buffer pool. The buffer pool is an array. Each slot stores a data file page. The indices of the array slots are referred to as buffer IDs. The buffer descriptors layer is an array of buffer descriptors. Each descriptor has one-to-one correspondent to a buffer pool slot and holds metadata of the stored page in the corresponding slot. Note the term buffer descriptors layer has been adopted for convenience, and it is only used in this document. Buffer table. The buffer table is a hash table that stores the relations between the buffer tags of stored pages and the buffer IDs of the descriptors that hold the stored page's respective metadata. 8.2.1 The buffer table. A buffer table can logically be divided into 3 parts: a hash function, hash bucket slots, and data entries. Hash function, bucket slots, data entries. The built-in hash function maps buffer tags to hash bucket slots. Even though the number of hash bucket slots is greater than the number of the buffer pool slots, collisions may occur. Because the number of hash bucket slots is greater than the number of buffer pool slots, collisions may occur. Therefore, the buffer table uses a separate chaining with linked lists method to resolve collisions. When data entries are mapped to the same bucket slot, this method stores the entries in the same linked list. A data entry comprises two values, the buffer tag of a page and the buffer ID of the descriptor that holds the page's metadata. For example, a data entry tag A ID 1 means the buffer descriptor with buffer ID 1 stores metadata of the page tagged with tag A. Hash function. The hash function is a composite function of calc_bucket and hash. The following is its representation in a pseudocode function. Unsigned int 32 bucket slot equals calc_bucket of the unsigned hash of the buffer tag, and the bucket size goes into calc_bucket. Note that the basic operations, lookup, insertion, deletion of data entries, are not explained here. These are very common operations that are explained in the following sections. 8.2.2 Buffer descriptor. The structure of buffer descriptor is described in this subsection. The buffer descriptors layer and the buffer descriptors layer in the next subsection. The buffer descriptor holds the metadata of the stored page in corresponding buffer pool slot, The buffer descriptor structure is defined by the structure buffer desc. While this structure has many fields, the main ones are shown below. Tag holds the buffer tag of the stored page in the corresponding buffer pool slot. Buffer ID. Buffer ID identifies the descriptor, equivalent to the buffer ID of the corresponding buffer pool slot. Ref count. Ref count holds the number of Postgres processes currently accessing the associated stored page. It is also referred to as pin count. When a Postgres process accesses the stored page, its ref count must be incremented by 1, ref count ++. After accessing the page, its ref count must be decreased by 1, ref count -. When the ref count is 0, i.e. the associated stored page is not currently being accessed, the page is unpinned, otherwise it is pinned. Usage count. Usage count holds the number of times the associated stored page has been accessed since it was loaded into the corresponding buffer pool slot. Note that the usage count is used in the page replacement algorithm. Context lock and IO in progress lock are lightweight locks that are used to control access to the associated stored page. These fields are described in section 8.3.2. Flags. Flags can hold several states of the associated stored page. The main states are as follows. Dirty bit. Dirty bit indicates whether the stored page is dirty. Valid bit. Valid bit indicates whether the stored page can be read or written, if it's valid. For example, if this page is valid, The corresponding buffer pool slot stores a page with this descriptor, valid bit, and this descriptor, valid bit, holds the page metadata. Thus, the stored page can be read or written. If this bit is invalid, then this descriptor does not hold any metadata. This means that the stored page cannot be read or written, or the buffer manager is replacing the stored page. I/O in progress bit. The I/O in progress bit indicates whether the buffer manager is reading or writing the associated page from to storage. In other words, it indicates whether a single process holds the I/O in progress lock of this descriptor. Free next. Free next is a pointer to the next descriptor to generate a free list. This is described in the next subsection. Note: the structure buffer desc is defined in source include storage buff internals.h. To simplify the following descriptions, these descriptor states are defined. Empty. When the corresponding buffer pool slot does not store a page, i.e. ref count and usage count are 0, the state of this descriptor is empty. Pinned. When the corresponding buffer slot stores a page and any Postgres processes are accessing the page, i.e. ref count and usage count are greater than or equal to 1, the state of this buffer descriptor is pinned. Unpinned. When the corresponding buffer pool slot stores a page, but no Postgres processes are accessing the page, i.e. usage count is greater than or equal to 1, but ref count is 0, the state of this buffer descriptor is unpinned. Each descriptor will have one of the above states. The descriptor state changes relative to particular conditions, which are described in the next subsection. In the following figures, buffer descriptor states are represented by colored box. So empty, white box means empty, a blue box means pinned, and a cyan box means unpinned. In addition, a dirty page is denoted as X. For example, an unpinned dirty descriptor is represented by a cyan box with an X in it. 8.2.3 Buffer descriptors layer. A collection of buffer descriptors forms an array. In this document, the array referred to as the buffer descriptors layer. When the Postgres server starts, the state of all buffer descriptors is empty. In Postgres, those descriptors comprise a linked list called free list. See figure 8.5. This is the initial state. Free list. Please note that the free list in Postgres is completely different in concept from the free lists in Oracle. Postgres's free list is only linked list of empty buffer descriptors. In Postgres, free space maps act as the same role of free lists in Oracle. Figure 8.6 shows how the first page is loaded. 1. Retrieve an empty descriptor from the top of the free list and pin it, i.e. increase its ref count and usage count by 1. 2. Insert the new entry, which holds the relation between the tag of the first page and the buffer ID of the retrieved descriptor in the buffer table. 3. Load the new page from storage to the corresponding buffer pool slot. Then 4. Save the metadata of the new page to the retrieved descriptor. The second and subsequent pages are loaded in a similar fashion. Descriptors that have been retrieved from the free list always hold pages metadata. In other words, non-empty descriptors continue to be used and do not return to the free list. However, related descriptors are added to the free list again, and the descriptor state becomes empty when one of the following occurs. First, if tables or indexes have been dropped. Second, if databases have been dropped. Or third, if tables or indexes have been cleaned up using the vacuum full command. Note: why empty descriptors comprise the free list? The reason why the free list is made, is to get the first descriptor immediately. This is a usual practice for dynamic memory resource allocation. The buffer descriptors layer contains an unsigned 32-bit integer variable, next victim buffer. This variable is used in the page replacement algorithm. 8.2.4 Buffer pool. The buffer pool is a simple array that stores data file pages, such as tables and indexes. Indices of the buffer pool array are referred to as buffer IDs. The buffer pool slot size is 8 kilobytes, which is equal to the size of a page. Thus, each slot can store an entire page. 8.3 Buffer Manager Locks. The buffer manager uses many locks for many different purposes. This section describes the locks necessary for the explanations in the subsequent sections. Please note that the locks described in this section are parts of a synchronization mechanism for the buffer manager. They do not relate to any SQL statements and SQL options. 8.3.1 Buffer Table Locks. Buff mapping lock protects the data integrity of the entire buffer table. It is a lightweight lock that can be used in both shared and exclusive modes. When searching an entry in the buffer table, a backend process holds a shared buff mapping lock. When inserting or deleting entries, a backend process holds an exclusive lock. The buff mapping lock is split into partitions to reduce the contention in the buffer table. The default is 128 partitions. Each buff mapping lock partition guards the portion of the corresponding hash bucket slots. Figure 8.7 shows a typical example of the effect of splitting buff mapping lock. Two backend processes can simultaneously hold respective buff mapping lock partitions in exclusive mode in order to insert new data entries. If the buff mapping lock is a single system-wide lock, both processes should wait for the processing of another process, depending on which started processing. The buffer table requires many other locks. For example, the buffer table internally uses a spin lock to delete an entry. However, descriptions of these other locks are omitted because they are not required in this document. Note: the buff mapping lock had been split into 16 separate locks by default until version 9.4. 8.3.2 Locks for each buffer descriptor. Each buffer descriptor uses two lightweight locks, content lock and IO in progress lock, to control access to the stored page in the corresponding buffer pool slot. When the values of fields are checked or changed as spin lock is used. (8.3.2.1) Content lock. The content lock is a typical lock that enforces access limits. It can be used in shared and exclusive modes. When reading a page, a backend process acquires a shared content log of the buffer descriptor that stores the page. However, an exclusive content log is acquired when doing one of the following: inserting rows, tuples, into the stored page, or changing the txmin, txmax fields of tuples within the stored page. txmin, txmax are described in section 5.2. Simply, when deleting or updating rows, these fields of the associated tuples are changed. An exclusive content lock is acquired when removing tuples physically or compacting free space on the stored page, performed by vacuum processing and hot, which are described in chapters 6 and 7 respectively. And an exclusive content lock is acquired when freezing tuples within the stored page. 8.3.2.2 I/O in progress lock. The I/O in progress lock is used to wait for I/O on a buffer to complete. When a Postgres process loads, writes page data from to storage, the process holds an exclusive I/O in progress lock of the corresponding descriptor while accessing the storage. 8.3.2.3 Spin lock. When flags or other fields, e.g. ref count and usage count, are checked or changed, a spin lock is used. Two specific examples of spin lock usage are given below. First example. The following shows how to pin the buffer descriptor. First, acquire a spin lock of the buffer descriptor. Increase the value of its ref count and usage count by 1, and then release the spin lock. 2. The following shows how to set the dirty bit to 1. Acquire the spin lock of the buffer descriptor. Set the dirty bit to 1 using bitwise operation. Release the spin lock. Note: replacing buffer manager spin lock with atomic operations. In version 9.6, the spin locks of the buffer manager can be replaced to atomic operations. See this result of commit fest. Oh, that sounds neat. Commit fest? I like that word. If you want to know the details, refer to this discussion. 8.4 How the buffer manager works. This section describes how the buffer manager works. When a backend process wants to access a desired page, it calls the read buffer extended function. The behavior of the read buffer extended function depends on 3 logical cases. Each case is described in the following subsections. In addition, the Postgres clock sweep page replacement algorithm is described in the final subsection. Eight 8.4.1 Accessing a page stored in the buffer pool. First, the simplest case is described, i.e., the desired page is already stored in the buffer pool. In this case, the buffer manager performs the following steps. 1. Create the buffer tag of the desired page. In this example, The buffer tag is tag C. And the compute hash bucket slot, which contains the associated entry of the created buffer tag using the hash function. Step 2. Acquire the buff mapping lock partition that covers the obtained hash bucket slot in shared mode. This lock will be released in Step 5. Step 3. Look up the entries whose tag is tag C and obtain the buffer ID from the entry. In this example, the buffer ID is 2. Step 4. Pin the buffer descriptor for buffer ID 2. i.e., the ref count and usage count of the descriptor are increased by 1. 5. Release buff mapping lock. 6. Access the buffer pool slot with buffer ID 2. Then, when reading rows from the page in the buffer pool slot, the Postgres process acquires the shared content log of the corresponding buffer descriptor. Thus, buffer pool slots can be read by multiple processes simultaneously. When inserting or updating or deleting rows to the page, a Postgres process acquires the exclusive content log of the corresponding buffer descriptor. Note that the dirty bit of the page must be set to 1. After accessing the pages, the ref count values of the corresponding buffer descriptors are decreased by 1. 8.4.2 Loading a page from storage to empty slot. In this case, assume that the desired page is not in the buffer pool and the free list has free elements, empty descriptors. In this case, the buffer manager performs the following steps. 1. Look up the buffer table, we assume it's not found. Create the buffer tag of the desired page. In this example, the buffer tag is tag E, and compute the hash bucket slot. Acquire the buff mapping lock partition in shared mode. Look up the buffer table, not found according to the assumption. Release the buff mapping lock. Then 2. Obtain the empty buffer descriptor from the free list and pin it. In this example, the buffer ID of the obtained descriptor is 4. Step 3. Acquire the buff mapping log partition in exclusive mode. This lock will be released in Step 6. Step 4. Create a new data entry that comprises the buffer tag E, and buffer ID 4. Insert the created entry to the buffer table. Step 5. Load the desired page data from storage to the buffer pool slot with buffer ID 4 as follows. Acquire the exclusive IO in progress lock of the corresponding descriptor. Then set the IO in progress bit of the corresponding descriptor to 1 to prevent access by other processes. Then load the desired page data from storage to the buffer pool slot and change the states of the corresponding descriptor. The IO in progress bit is set to 0 and the valid bit is set to 1. And then release the IO in progress lock. Step 6. Release the buff mapping lock. Step 7. Access the pool slot with buffer ID 4. 8.4.3. Loading a page from storage to a victim buffer pool slot. In this case, assume that all buffer slots are occupied by pages, but the desired page is not stored. The buffer manager performs the following steps. Step 1. Create the buffer tag of the desired page and look up the buffer table. In this example, we assume the buffer tag is tag M. The desired page is not found. Step 2. Select a victim buffer pool slot using the clock sweep algorithm. Obtain the old entry, which contains the buffer ID of the victim pool slot, from the buffer table and pin the victim pool slot in the buffer descriptors layer. In this example, the buffer ID of the victim slot is 5, and the old entry is tag F, ID 5. Step 3. Flush. Write and fsync the victim page data if it is dirty. Otherwise, proceed to step 4. The dirty page must be written to storage before overwriting the new data. Flushing a dirty page is performed as follows. First, acquire the shared content lock and the exclusive IO in progress lock of the descriptor with buffer ID 5, released in step 6. Then, change the states of the corresponding descriptor, the IO in progress bit set to 1, and the just dirtied bit set to 0. Then, depending on the situation, the xlogflush function is invoked to write the wall data on the wall buffer to the current wall segment file. Details are omitted. Wall and xlogflush function are described in Chapter 9. Then flush the victim page data to storage and change the states of the corresponding descriptor, the IO in progress bit set back to 0 and the val bit set to 1. And then release the IO in progress and content locks. Step 4. Acquire the old buff mapping lock partition that covers the slot that contains the old entry in exclusive mode. Step 5. Acquire the new buff mapping lock partition and insert the new entry to the buffer table. This is done by creating the new entry comprised of the new buffer tag, tag M, and the victim's buffer ID. Then, acquire the new buff mapping lock partition that covers the slot containing the new entry in exclusive mode. And finally, insert the new entry to the buffer table. JK. Step 6. Delete the old entry from the buffer table and release the old buff mapping lock partition. Step 7. Load the desired page data from the storage to the victim buffer slot. Then update the flags of the descriptor with buffer ID 5, and the dirty bit is set to 0, and initialize other bits. Step 8. Release the new mapping lock partition. Step 9. Access the buffer pool slot with buffer ID 5. 8.4.4 Page replacement algorithm, clock sweep. The rest of this section describes the clock sweep algorithm. The algorithm is a variant of not frequently used with low overhead. It selects less frequently used pages efficiently. Imagine buffer descriptors as a circular list. Figure 812. The next victim buffer, an unsigned 32-bit integer, is always pointing to one of the buffer descriptors and rotates clockwise. The pseudocode and description of the algorithm are as follows. 1. Obtain the candidate buffer descriptor pointed to by next victim buffer. 2. If the candidate buffer descriptor is unpinned, proceed to step 3. Otherwise, proceed to step 4. Step 3. If the usage count of the candidate descriptor is 0, select the corresponding slot of this descriptor as a victim and proceed to step 5. Otherwise, decrease this descriptor's usage count by 1 and proceed to step 4. Step 4. Advance the next victim buffer to the next descriptor. If at the end, wrap around, and return to step 1. And repeat until a victim is found. 5. Return the buffer ID of the victim. A specific example is shown in figure 812. The buffer descriptors are shown as blue or cyan boxes, and the numbers in the boxes show the usage count of each descriptor. Clock sweep. 1. The next buffer pointer points to the first descriptor, buffer ID 1. However, this descriptor is skipped because it is pinned. 2. The next buffer points to the second descriptor, buffer ID 2. This descriptor is unpinned, but its usage count is 2. Thus, the usage count is decreased by 1, and the next victim buffer advances to the third candidate. 3. The next victim buffer points to the third descriptor, buffer ID 3. This descriptor is unpinned, and its usage count is 0. Thus, this is the victim in this round. Whenever the next victim buffer sweeps an unpinned descriptor, its usage count is decreased by 1. Therefore, if unpinned descriptors exist in the buffer pool, this algorithm can always find a victim, whose usage count is 0, by rotating the next victim buffer. 8.5. Ring buffer. When reading or writing a huge table, Postgres uses a ring buffer rather than a buffer pool. The ring buffer is a small and temporary buffer area. When any condition listed below is met, a ring buffer is allocated to shared memory. 1. Bulk reading. When a relation whose side exceeds 1/4 of the buffer pool size, shared buffers divided by 4, is scanned, in this case, the ring buffer size is 256 kilobytes. Bulk writing. When the SQL commands listed below are executed, in this case, the ring buffer size is 16 megabytes. Copy from, create table as, create materialized view or refresh materialized view, alter table command. 3. Vacuum processing. When an auto vacuum performs a vacuum processing, in this case, the ring buffer size is 256 kilobytes. The allocated ring buffer is released immediately after use. The benefit of the ring buffer is obvious. If a backend process reads a huge table without using a ring buffer, all stored pages in the buffer pool are removed, kicked out. Therefore, the cache hit ratio decreases. The ring buffer avoids this issue. Why the default ring buffer size for bulk reading and vacuum processing is 256 kilobytes? Why 256 kilobytes? read the README. For sequential scans, a 256 kilobyte ring is used. That's small enough to fit in an L2 cache, which makes transferring pages from OS cache to shared buffer cache efficient. Even less would often be enough, but the ring must be big enough to allocate all pages in the scan that are pinned concurrently. 8.6 Flushing dirty pages. In addition to replacing victim pages, the checkpointer and background writer processes flush dirty pages to storage. Both processes have the same function, flushing dirty pages. However, they have different roles and behaviors. The checkpointer process writes a checkpoint record to the wall segment file and flushes dirty pages whenever checkpointing starts. The role of the background writer is to reduce the influence of the intensive writing of checkpointing. The background writer continues to flush dirty pages little by little with minimal impact on database activity. By default, the background writer wakes every 200 millisecond, defined by PG writer delay, and flushes PG writer least recently reused max pages at maximum, and the default for that is 100 pages. Note: why the checkpointer was separated from the background writer. In version 9.1 or earlier, background writer had regularly done the checkpoint processing. In version 9.2, the checkpointer process has been separated from the background writer process. Since the reason is described in the proposal whose title is Separating BG Writer and Checkpointer, the sentences from it are shown in the following. Currently, in 2011, the BG process performs both background writing and checkpointing and some other duties. This means that we can't perform the final checkpoint fsync without stopping background writing. So there is a negative performance effect from doing both things in one process. Additionally, our aim in 9.2 is to replace polling locks with latches for power reduction. The complexity of the BG writer loops is high, and it seems unlikely to come with a clean approach using latches. That's it for Chapter 8. I'll be right back with Chapter 9.